Welcome back, everybody. In this video, we're continuing with section 3.2, looking at measures of variation, specifically the standard deviation for now. This part we had seen at the end of last time. We had looked at some important properties of the standard deviation. The important fact first is that it measures how much the data values varies away from the mean. Okay. So also, just as a reminder, we only want to compare two standard deviations when the sample means are approximately the same. Okay, if the means are wildly different, then it doesn't make a lot of sense to compare their standard deviations, as we'll see in an example later on. All right, so that was old. So here's where we're actually starting something new. We want to look at something called the range rule of thumb that is used for approximating the standard deviation. So this is based on the principle that for a lot of data sets, it turns out that about 95% of the data lies within two standard deviations of the mean. For example, if we were to take all of the students in this class, let's say, and measure everyone's height and find the mean, and then find the standard deviation, and then organized everybody, we would find that 95% of you, your heights, would fall within two standard deviations of the mean. There would be some people really tall, some people who are really on the shorter side, but about 95% of the data, or 95% of your heights, would lie within two standard deviations of the mean. Okay, so, and that's true for a lot of data sets, as it turns out. So basically, a way to put this kind of in algebra-like format is to say that the largest usual or typical value you might see is the mean plus two standard deviations. And then the smallest usual or typical or commonly occurring value might be the mean minus two standard deviations. Okay, so another way, yet another way to think about that would be to think, okay, let's say that we had a number line, and then we would have the mean sitting on the number line. If we wanted to go up to the mean plus two standard deviations, and then down to the mean minus two standard deviations, that interval would contain about 95% of the data. Okay, so the biggest value that you're likely to run across, or commonly occurring value, would be two standard deviations above the mean. The smallest value, your usual value, or commonly occurring value, would be two standard deviations below the mean. So that's what these two equations, basically in blue, are referring to. Okay, so then if we were to subtract the two equations from one another, as is commonly done in algebra class, the largest usual value minus the smallest usual value is going to equal the mean plus two standard deviations minus the mean minus two standard deviations. So then, simplifying that right side, distributing the negative, okay, there's your algebra prerequisite, okay, distributing the negative, we'll see that there's minus the mean, and then minus a minus will make plus two standard deviations. So in all, the two means add up to 0, and we're left with 4 standard deviations. So what does that mean? The largest usual value minus the smallest usual value should equal about 4 standard deviations. Okay, considering that captures 95% of the data, then we would only expect a little bit more to be beyond that 2 standard deviations above or below the mean. So then we could take the range, which we learned last time was the maximum minus the minimum, which isn't necessarily the same as the x bar plus or minus 2 standard deviations, but we could take the range, and that turns out that it's about 4 standard deviations. So if we take the range divided by 4, that is going to be approximately the standard deviation. Okay, and that's what's called the range rule of thumb. Okay. And I just realized, in case the term is not familiar to you, what a rule of thumb is kind of an everyday guideline or a familiar fact or familiar rule you can use to calculate something. So rather than using the exact formula for standard deviation, if all you're looking for is an approximation, the range rule of thumb can be used to say, okay, well, the standard deviation is about or approximately some value. It has the advantage that it's easy to calculate. You take the range and divide by 4. Of course, that won't give you exactly the standard deviation, but sometimes we can use it as a replacement for it. All right, so moving along. So we wanted to do a couple of problems from the textbook next. So here it says, based on data set 1 in Appendix B, females have pulse rates with a mean of 77.5 beats per minute and a standard deviation of 11.6 beats per minute. We want to know if it's unusual for a female to have a pulse rate of 99 beats per minute. So here what they mean by unusual is rare, okay? And so we're going to do that by figuring out whether or not that 99 beats per minute lies within 2 standard deviations of the mean. So a picture is always a good idea, especially as you are just starting out. So I'm going to put the mean in here. The mean is 77.5 beats per minute. Then we'll have the mean plus 2 standard deviations. That will be 77.5 plus 2 11.6s. Okay, and then we're interested in 99 beats per minute. So we don't need the low end, but just for practice's sake, I'm going to go ahead and put in the mean minus 2 standard deviations. So that will be 77.5 minus 2 times 11.6. Okay, so let's calculate those things. All right, so going through the calculations, it looks like if we go up 2 standard deviations, that would take us to 100.7 beats per minute. Considering that we're interested in an individual having a pulse rate of 99 beats per minute, that's still within the interval of what we would consider basically to be not unusual, in that it would capture 95% of the individuals. So as long as a woman's pulse rate is between 54.3 and 100.7, that would make up 95% of individuals. So it's not unusual in that sense. Okay, so no, basically it's not unusual. We could say it's not unusual in the sense, sorry, my pen went wonky on me. In the sense that the interval 54.3 up to 100.7 contains 95% of individuals. Okay. All right, so let's try that again. So here it says, based on data set 1 in Appendix B, males have pulse rates with a mean of 67.3 beats per minute and a standard deviation of 10.3 beats per minute. And same basic question, we want to know if it's unusual for a male to have a pulse rate of 45 beats per minute. That sounds low, but is it that low? So let's find out. So pause the video at this point and try to do yourself what we just did a minute ago for the women. See if you can replicate that for the men and come to a decision about whether or not that is an unusually low pulse rate. All right, so let's see how that's going to go. So again, I would start by drawing a number line. The mean was 67.3 beats per minute. And then let me go ahead and lower that. That's where the mean will be. And then we'll have the mean plus 2 standard deviations, the mean minus 2 standard deviations, So we'll have 67.3 plus 2 times 10.3. Then we'll have 67.3 minus 2 10.3s. All right, so what we're going to want to do is calculate those, and then we need to decide if 45 beats per minute lies inside or outside that. All right, so going through the calculations, it turned out that our interval was ranging between 46.7 beats per minute and 87.9 beats per minute. So we wanted to decide if we had an individual with a pulse rate of 45 beats per minute, is that going to be unusual? So it turned out, yes, that is unusual in the sense that it's in the most extreme 5% of pulses, some high and some low, but it's definitely not in the interval that contains 95% of pulse rates. All right, so that takes care of that example. So next up, we want to remind you about population standard deviation. So we had seen this in the last video. Here in light blue, we have the formula for the sample standard deviation. Note again that this formula is going to involve x bar, which is the sample mean. And there's also a division by n minus 1, which improves the approximation of sigma by s. And then we have sigma, the population standard deviation. In its formula, we're going to have mu, the population standard deviation. And then in the division, we just have division by n, capital N, which is the size of the population. All right, so we have seen standard deviation. I did want to mention also the variance. So the variance for a data set is basically kind of like the standard deviation, but where we don't take the square root. So in terms of the formula, it's called either sigma squared or s squared, depending on whether you're talking about a population or a sample. For the population, it's going to be the sum of x minus mu squared all over capital N, but without the square root on it. And then for s squared, which is the sample standard deviation, you will have the sum of x minus x bar all squared, and that's divided by little n minus 1, one less than the sample size. Okay, so most often the standard deviation is used, but we do want to mention the variance because it does come up. There are some important properties of variance that we would like to see next. Okay, so one thing that is important is that the units for the variance are the squares of the units of the original data values. So if your data values are, let's say, heights of people in inches, then the units for the variance will be in square inches, which is an area, not a height. So you want to be aware of that. Units for the variance are the squares of the units for the data values. Okay, the value of the variance can increase dramatically with the inclusion of one or more outliers. We saw that the standard deviation was sensitive to outliers because it's built around the mean. The variance in a way is the same, but is even worse because it's squared. And as you know, if you square things, start going around squaring numbers, they get really big really fast. So if you introduce outliers, then that can really influence the variance. Okay, the value of the variance is usually positive, it's never negative. It could be 0 only when all the data values are equal. And usually we don't study data sets like that because if the data values are all the same, then there's not a lot to say about it. Okay, the sample variance S squared is what's called an unbiased estimator of the population variance sigma squared. So what that means down here in red is that the sample variance closely approximates or closely tracks the population variance. We saw that the sample standard deviation doesn't track or approximate the population standard deviation as well. Remember that one of our big goals for this course is to be able to use sample data to say something about a population. So in that sense, that's something more valuable for the variance is that it does track, the sample variance tracks the population variance more closely. Okay, all right, so the next part has to do with the empirical rule. This is kind of a big topic. We'll spend chapter 6 basically talking about this, and we're kind of warming up to the idea here. We saw with the kind of in the discussion of the range rule of thumb that about 95% of the data lies within 2 standard deviations of the mean. This part, we're talking more about that. So you've heard of a bell curve before, probably in discussions of IQ and perhaps test scores as well. So this has to do with that also. A lot of data sets do have this kind of characteristic bell shape to them, which is what's called a normal distribution. And if you have a set of data that does have this distribution, that is, the data is distributed in this way, it turns out that about 68% of the data will lie within one standard deviation. About 95% of the data will be within two standard deviations. I've marked that here with the yellow arrow because that was familiar from before. 95% within two standard deviations, 68% of the data within one standard deviation, and then almost all of it, or 99.7% of the data within three standard deviations of the mean. Okay, and then we can exploit some symmetry that this distribution has. The mean is always at the center, okay? X bar, in this case, X bar is always at the center of the distribution. And so if 68% of the data is within one standard deviation, that means about half of it, or around 34, would be on either side. It turns out that it's 34.13. So here up top in the graphic, this is taken from the textbook. In the graphic, they just rounded this a little bit. This 68% could have been 68.26%. They just didn't show that many decimals. That's why it doesn't totally match what you have down here, the 34.13. 34.13 twice is 68.26%. Okay, and then you're going to have the same thing happening as well. The total of 34.13% and 13.59% times 2, that is this plus this plus this plus this, should equal about 95%. It turns out to be closer to 95.44%, but we won't concern ourselves with that difference at this moment. Okay, so the distribution does have some symmetry. We know that 95% of the data is within two standard deviations, so that means that about 47% is going to be between the mean and two standard deviations above the mean. Okay, if 99.7% of the data is within three standard deviations of the mean, then 0.3% would be in the two tails. If you take 0.13% plus 0.13% and add them up, you get 0.26%, right? And they've rounded that up to get the 0.7, or 1 minus that 0.7%. So sorry, they've kind of played fast and loose with the decimals here, but you do want to kind of just think of this as the 68, 95, and 99.7% of the data within 1, 2, and 3 standard deviations of the mean. In order to make conclusions about this, the empirical rule, which is that 68, 95, 99.7, the distribution does need to be approximately bell-shaped. If it's not, then you can't say things like what we just did about the 68, 95, and 99.7. Okay, so how can you use it? Let's try some examples. Suppose that it is known that IQ scores are approximately normally distributed with a mean of 100 and a standard deviation of 15. Let's say we'd like to know what percentage of IQ scores is over 130. So let's say you took an IQ test, it came back 130, and so you want to know, okay, well, how special am I? Okay, what percentage of IQ scores is over 130? So as you're going to do this, it's tempting not to, but as you're going to do this, it's a good idea to try to draw and label a normal distribution. It doesn't have to be really beautiful or anything, but you do have to be able to read it. So the mean is at the center of the distribution. We're interested in what percent of IQ scores is over 130. So 130 is here. I'd like to know what percentage of IQ scores is in that upper end. So in order to do that, I should know how far is 130 over 100 in terms of standard deviations. So 130 minus 100 is, of course, 30. And we're told that the standard deviation is 15. Okay, and how many times does 15 go into 30? Twice, right? So that is 2 standard deviations. I'm abbreviating that by SD, okay? SD is standard deviation. Let me write that in here. All right, so 130 is 2 standard deviations above the mean. All right, so we need to take a look, think about this, and take a look at our chart perhaps. We know that 95% of the data is within 2 standard deviations of the mean. That means that in the 2 tails, we would have the rest of it, which would be 5% of the data, right? So 5% of the data is in the 2 tails. Using symmetry, then half of it would be in the upper half tails. So that is 2.5% of the data. So 2.5% of the IQ scores are over 130. Okay, so here this is basically rounded. You don't get the exact same value as you do here. Unfortunately, the way that they've stated this. But if you look in the right tail beyond the 2 standard deviations, you get 2.14% plus 0.13%, and that is 2.27%, and that's not the same as 2.5. It's a 1/4% off, and that's due to the rounding again that they have done. So, but concept-wise, that is the part of the distribution that we're looking at. Okay, so now let's say that we'd like to know what percentage of scores lies between 70 and 100. So let's try that. So once again, let me draw a little picture of this. It's a good practice to draw the picture. It helps you understand, in my opinion. And also, when we have more complicated situations later on, we'll rely on the picture more. Let's just leave it at that for right now. So it's good to get in the habit of making the picture. All right, so there's our mean at 100 and then 70 to 100. We wanted to know what percentage of IQ scores falls in that range in between 70 and 100. So I know that the mean is 100, and then what's the difference between 70 and 100? Well, it's 30, right? And 30 is, again, 2 standard deviations. This is on the lower end this time, unlike the last time, but this time it is on the lower side. So this is the mean minus 2 standard deviations. Okay, so we know from our earlier work that if we were to go 2 standard deviations above or 2 standard deviations below, that would capture 95% of the data. Okay, here we're looking just in the lower part of that. So instead of going from 70 to 130, which would be 2 standard deviations above and below, we're going below only. So that'll be half of 95%, and then that's 47.5%. Okay, so what this means then is about just a little under half, or 47.5% of these IQ test takers have IQs between 70 and 100. All right, so we have another example here from the textbook. This one is about body temperatures. It says body temperatures of healthy adults have a bell-shaped distribution with a mean of 98.20 degrees Fahrenheit and a standard deviation of 0.62 degrees Fahrenheit. Using the empirical rule, which is again that 68, 95, 99.7% rule, we want to know the approximate percentage of healthy adults with body temperatures, and then there's 2 parts to this question. So we want, first of all, within 1 standard deviation of the mean, which is 97.58 to 98.82 degrees Fahrenheit. Here they've gone ahead and told us that it's 1 standard deviation above and below the mean. And so we know that that's 68% of the temperatures. Okay. And so just to kind of confirm, just to make sure that we know where that's coming, these two values came from, 97.58 minus 0.62 is 96.96. No, 97.58, 0.62. There we go. Okay, so that, hang on a second. All right, sorry about that. I was confused for a second. So the 97.58 is the mean minus 1 standard deviation, and the 98.82 is the mean plus 1 standard deviation. That's where they got the 97.58 and the 98.82 from. So that turns out to be helpful to know for the second part of it. We want to know between 96.34 degrees and 100.06 degrees. So we want to figure out how many standard deviations that is. We know that the mean is 98.2 degrees Fahrenheit. I'm going to leave off the degrees Fahrenheit symbol just so that the picture is less cluttered. Okay, keep in mind that that's what the values are, is degrees Fahrenheit. All right, so the upper end was 100.06. And then the lower end is going to be down to 96.34. Okay, so we need to know what that is. So the 100.06 minus 98.2, 100.06 minus 98.2 is 1.86. And then 98.82 minus 96.34 is going to be 2.48. No, I mistyped it. It's 1.86. Had to be 1.86 both times. Sorry about that. Okay. All right. So the thing is that 1.86 is 3 standard deviations. This 1.86 is 3.62s. So this is within 3 standard deviations of the mean. So here we have X bar. This is X bar plus 3 standard deviations. This is X bar minus 3 standard deviations. So we know from looking at the empirical rule that that would be 99.7% of the data. So 99.7% of values fall in that range. All right, so here's one for you to try. Here it says the data set is approximately bell-shaped with a mean of 34.2 and a standard deviation of 3.1. We want to know what percentage of the data lies between 31.1 and 40.4. So you should pause the video and try this yourself. You want to draw the bell curve and then label the mean and then the upper and lower limits, the 40.4 and 31.1, and try to figure out how many standard deviations above and below the mean those are, and then refer to that empirical rule to help decide what percentage of the data lies in that interval. So pause the video and give that a try. All right, so going through the calculations there, it looks like the difference between the upper limit and the mean is 6.2, and our standard deviation was 3.1. So that is 2 standard deviations. Between 34.2 and 31.1 is a distance of 3.1, which is 1 standard deviation. So what's different about this example from the earlier examples that we'd had is that the interval around the mean is not symmetric this time. So in between the mean and 31.1, we saw that that was one standard deviation down. So about half of 68, so like 34, or here we'll use it off the picture, 34.13% of the data lies between the mean and a 0.1 standard deviation below the mean. For the upper end, that's a distance of 2 standard deviations. So it will be the 34.13 plus the 13.59%. So 34.13 plus the 13.59%. So let's add that up. That's 47.72%. Okay, so in all, 81.85% of the data. Okay, so again, what's different about this example and the earlier examples we have done is that the interval is not symmetric around the mean. All right, so that takes us to the end of this part of section 3.2. In the next part, we're going to do another example, and then we're going to go on to something called the coefficient of variation. And so in the meantime, let me know if you have any questions, and have a great day.